Good morning, everyone. Welcome back to the second day of CalPlug 15th anniversary workshop. This year's theme is on energy efficiency, greenhouse gas emission, plug load nexus. And this is the second day of the workshop to celebrate the Earth Day 50th anniversary. So I would like to take this opportunity to thank all the distinguished speakers for their contribution to the success of the program. Also, I want to thank all the audience who dialed in to join us in celebration of the Earth Day. I know it is very challenging and difficult time for most of us in facing the virus pandemic. And your willingness to participate and contribute to this workshop and give us the feedback comment are highly appreciated. And lastly, I want to thank my staff. While I'm staying at home, they are essential workers and to make the program available to all of us. So I want to thank them as well. So at this time, I'd like to remind the speaker, within the last 2 minutes of your presentation, I will give you a warning sign and say you have 2 more minutes to wrap up. So after the presentation, if we have time, we will have the Q&A session, allow the audience to ask questions. The way we are going to handle the question is the following. For the audience, if you have a question, please send the in the chat room a message to us, and I will receive the message and read it out to the speaker and at the end of their presentation. So this is how we are going to run today's workshop. And at the end, I will have the wrap up. At this time, I'd like to introduce the first speaker, Wendell Brase. He is our very own Earth Day hero and keynote speaker in University of California, Irvine. He is the first UC Irvine's Associate Chancellor for Sustainability. In this role, he leads effort by UC Irvine and assists other campuses throughout the UC system to implement UC's carbon neutrality initiative. Wendell, please take away.
Wendell. Okay, can you hear me now?
Yes.
Okay, good. Sorry, it took me a second to figure out what I was doing there. Let me see if I can minimize my own picture so I can see my slides. There we go. Okay, this seems like a good day to reflect back on what we've learned since 2007. Why that date? It was in about November, I guess it was November 2007, when all the chancellors of all the UC campuses together made the commitment to become carbon neutral. They joined something called the ACU-PCC, the American College and University President's Climate Commitment. And we had to figure out how to rise to that challenge. It was an important challenge for environmental reasons. Technically, we didn't quite know what we were going to do. So I'm going to tell you what we did and what we've learned in the process. By the way, some of my slides will have, they'll be pretty dense in terms of information. They're all available to anyone who's interested afterwards. Just send us a note and we'll share anything. So in 2010, a group that I had the privilege of chairing wrote this report. This is a UC report, not a UC Irvine report. So it lays out the framework for the whole UC system to become carbon neutral. It basically is kind of simple. It has 3 parts. Part 1 is minimize demand through efficiency. That seems like principle number 1. And actually, frankly, at that point in time, that was the only thing we knew how to do for sure. We had been doing some energy efficiency. We thought we could ramp it up. We thought it was important. Then we had, at that time, and still do, 7 locations within the UC system that rely on natural gas for their cogeneration plants. Very substantial investment has been made in those plants. And to decarbonize them, we would have to develop a directed biogas. And so we set a goal to procure biomethane to mitigate our entire Scope 1 emissions. And then Scope 2 emissions, which was the electricity we were procuring then and now from the grid, to develop a plan to become entirely carbon neutral. And I won't talk about that very much today because that has actually been achieved. As this report proposed, UC formed an actual utility, which is called the Energy Services Unit. It has procured energy across the system that is coming in as Scope 2. It's all carbon neutral now, and now they're turning their attention to Scope 1 emissions, i.e. Decarbonizing the gas supply for UC. So deep energy efficiency, we adopted this idea. It's a word we picked after we heard it from friends at Berkeley and Davis. So this is kind of a joint effort in a lot of ways. The goal we picked was to try to achieve on energy efficiency retrofit projects 50% savings, to cut energy use in half for projects. Now, keep in mind, back in 2010, a good energy project, good energy efficiency project would be one that was saving 10%. It was really outstanding if it saved 50%. Well, we picked 50. And we also picked a similar goal for new construction. Why? Because at that time, and still for that matter, UC Irvine was growing, and we were just going to dig a deeper and deeper hole to get out of in terms of carbon neutrality if we didn't build the most efficient buildings possible. So we set the goal of beating California's Title 24, which many of you know is considered the toughest energy code in the United States, beat it by half. How? We were going to make the building smart. We're going to make the campus smart. I'll talk about that in just a second. So why did we do this? Again, first principle, reduce. Second principle was we didn't know how much decarbonized energy would ultimately cost for the University of California or for this campus, but we knew it was going to cost more. It just has to. So we figured that the best way to pay for the ultimate cost of decarbonized energy is to save as much as possible, to use as little as possible, and to use that savings once those projects are paid off to then pay for the added cost increment that we think will come with decarbonization. So it's a plan that actually has a financial principle behind it as well. What's a smart building? One of the key features is what's called demand-controlled HVAC, heating, ventilating, and air conditioning. This means that our air conditioning is not just controlled by thermostats or by timers, as it used to be. It's controlled by sensors. And so, for example, in a lecture hall, we're sensing not just whether there are people in there, we're sensing what the CO2 level is in the return airstream. In laboratories, we're sensing more sophisticated things like particulates down to a very small level. We're sensing VOCs, volatile organic compounds, which is very important in laboratories for safety. And so then we're right-sizing air changes based upon real-time sensors. And we have to have a lot of HVAC zones to do this because it's not just for a whole building that you do this, it's zone by zone by zone by zone. So in a building like a science building, we'll have thousands of sensor points. New buildings being built right now, thousands of sensor points. Whole campus now, 465,000 data points being measured as we speak every 5 seconds. That's a smart campus. And it means that demand control has reduced energy, and I'll show you how much in just a minute. High quality lighting that has high color rendering index, that's what CRI stands for, as well as being more efficient. That's an important part of this because that is a heat load. We're trying to reduce air conditioning costs. So that has a co-benefit of reducing heat load as well as improving quality. So yeah, here's what happened. This is the numbers we got after we were into this deep energy efficiency program about 5 years. So this is about half of the last decade. We were seeing results like this. Remember, our goal overall for the campus was 50%. Well, these numbers average them out. Labs are a big deal on a university, research university campus. They consume so much energy that that making a big dent in that area was a key part of our strategy. And you'll see what I mean in a second. We also knew that as we were building new buildings, we had to build them to exemplary energy efficiency standards. These are the standards we used. We've actually been using these standards for a couple of decades, and they have been upgraded twice to make them more rigorous. I won't go through all these things, obviously, but as I say, you're welcome to have this slide. Many campuses across the country now are using this slide. And actually, a couple of universities in China are now probably ramping up to use these energy performance requirements in lab buildings. And this isn't just lab buildings. This actually talks about other kinds of buildings as well. But you see here, it's about air changes. It's about total static losses in an HVAC system. It's about the density of illumination power and things like fume hoods and heat generating exhaust and so on. So the point here is it's a holistic approach. One has to do all these things to achieve the kind of energy performance that we're aiming for in new buildings. This is a chart we actually started a long time ago, back in the early 90s. The blue line on this chart is what our energy consumption for the whole campus would have been if we just continued through the 90s and beyond to build buildings to code and maintain them reasonably well. The green line's what actually happened. So we started out, you see there, by adopting the tag there where the arrow says in 1991, we adopted this goal of beating Title 24 by 30% in new construction. So you don't see that right away. You see it a couple of years later because you have to then apply that principle, build the buildings, measure them, and then so the actual performance lags a little bit in the green line. So the green line is actually what happened as we did things along the way. What happened in 2007? Remember, that was the year when we adopted becoming carbon neutral as a University of California-wide commitment. Look at this. So that's when we also adopted this idea of deep energy efficiency. And a few years later, we joined President Obama's Better Buildings Challenge. Look what happened. 50% savings in about 2 decades. In other words, the campus, said differently, the campus has doubled in size in a couple of decades, 2 decades, and it's using the same amount of energy. That's what deep energy efficiency can do. Some people still don't believe this is feasible. It's possible. But we're trying to spread the word. There are also many co-benefits besides the direct energy benefits I just showed you. In the process of doing complete energy retrofits on many buildings, all of our lab buildings, for example, we found deferred maintenance problems that had probably gone unfunded for decades. Some of them were undiscovered for decades. And so they were actually funded using energy savings. That's a big deal. The information layer, the whole informatics structure behind this system, which is basically, if you think of it this way, it's the system you need to keep a smart building smart or a smart campus smart. That really has a lot of co-benefits. Lighting quality is improved, buildings are quieter, they're cleaner inside. The reason they're cleaner is because we're now able to use a really high quality air filtration standard. We use filters that are just 1 notch short of a HEPA filter. Well, you could never use those until you slow down the air enough that the penalty you pay for the resistance of air filtration in an HVAC system goes almost to 0 with the reduced air change speeds that we're using. Laboratories are safer. We have a more reliable research infrastructure. These are big things for a research university. So the co-benefits were way more than we expected when we started out. Other lessons learned, there's something about changing the culture that goes way beyond what you can do at the margin. When you think differently, it is amazing how much different the results can be. Deep energy efficiency was feasible. Our suspicions were right. All kinds of waste had been designed into mechanical systems. They've been called best practices for 20, 30, 40 years in some cases. The big game changer was sensors and software. That's what made it all work. And in some cases, we got nonlinear savings, by the way. In other words, physics helped out in some cases. For example, those exhaust fans that you may see on the top of some of our research buildings that exhaust air from a laboratory building, for those, they follow something called the cube rule. That means when you cut the airspeed of the exhaust in half, which we've done for all of our buildings, and in some cases by making the fume hood stacks a little bit higher on top of the buildings, cut it in half, you save 7/8. This is how we get numbers like the ones I just showed you. People say all the time, I read this at least someplace or another every single week. I read that smart buildings ought to be providing demand response opportunity. You know, there's no evidence for this, but people keep saying it. I guess it seems intuitively correct. But remember, what smart buildings are is precision control of energy. What do I mean by that? Precision control is using sensors and software in the way I've just been generalizing to deliver just the right amount of energy at just the right place at just the right time. That means in a perfectly smart building, all the kinds of energy waste that have been designed in the first place have been discovered and controlled with sensors and software, so they don't exist. You can't turn them down when you get some kind of a control signal. What does work is something like our bus fleet. Now this fleet, 20 buses, when they're all charging at night, and they charge at night because they use them during the day, at night they add up to 4 megawatts when they're all charging. And that's a good thing because we actually need the load at night because we've slowed down our cogenerators so much by all the smart buildings now that the load goes too low. Well, these actually are a good load management tool for us. Let's see, there's another load management tool that does actually work. That big thermal storage tank, that big tank you see over by the central plant is 4.5 million gallons of chilled water, chilled to 38 degrees. Well, the amount of energy it takes to store that, to rather chill that water to 38 degrees for that whole tank is 40 megawatt hours. If that were a battery, it would be one of the hugest batteries in California. It makes a lot of sense to use your storage medium as a thermal medium if that's the end use. So that's why this makes a lot of sense. Oh, here's a picture of it with the anteater painted on it. This is just saying the best form of energy storage may not be a battery. It means that in that duck curve you see over on the right, we can shift our load anytime we want in a 24-hour day, because when that tank's fully charged to 38 degrees, you can run the whole campus on the hottest day of the year without running a chiller at all. It allows you to move that load around to do load management at the enterprise level, not the building level. That's quite different. Now, we're actually working with a Cal State campus, and if this works on one campus in Cal State, I think it will be extrapolated out to all their campuses. The idea here is, this is a curve probably most of you have seen. This is the California duct curve. It's from the Cal ISO, California Independent System Operator. It shows 2013, 14, 15, 16, 17, and so on. What's happening is the net load in California is getting lower and lower. The duct, what I call the belly of the duct curve, is getting deeper and wider every year as more renewables are added to the grid. And so much so that now renewables are being curtailed almost every day of the year in California. And that's certainly going to happen as we add more renewable penetration to the California grid. So the idea is to take big thermal storage tank like the one I just showed you, and maybe a second one for hot water, in a campus that has a lot of chillers, and they'll have to add some chillers and add some heat pumps. Charge those tanks only at the middle of the duct curve, or anytime in that duct curve when you can add load, because adding load in the bottom of the duct curve uncurtails renewable power, which is otherwise curtailed. It will all be green power. The first CSU campus that does this will become more than 50% carbon neutral on day one when they do this. This concept really holds a lot of potential. So this will be interesting. We're not going to do this on our campus because we have a different kind of infrastructure as I just mentioned. But this is an example of how we're working with other campuses, and in this case, Cal State. So more subtle lessons. Well, you know, technology was important for a lot of what we did, but attitude was actually equally important. I always say, if you look at everything we've done in the last decade, attitude was 51%, technology was 49%. The attitude is, oh, that's called a best practice. Let's take another look at that. That's the kind of attitude on the part of engineers that actually break through and make remarkable savings. We discovered that information layer is more important than we initially thought, and now we see why. The demand response concept, as I just described, has changed quite a bit from what we used to think. It requires an enterprise solution. Batteries may not be the best solution. So these are more subtle lessons that we learned. Now going back to this, the second part was biomethane, developing biomethane. This has turned out to be a little tougher than we initially thought for these reasons. If you put out an RFP for biogas, you won't get 20 solid proposals within a week the way you will if you put out an RFP for, let's say, a solar project. It's not as mature a market. Natural gas prices have been at a prolonged, real low price, and that has made it more difficult to develop this. The infrastructure costs are pretty high. The photographs here I'm showing you are actual photographs from the UC project, the first big biogas project, which is capturing biogas coming off a big landfill in Shreveport, Louisiana. And this is the processing that has to go through landfill gas. It comes out of the ground with contaminants, so they have to be filtered out. There's a certain amount of moisture content that has to be removed. There are a whole set of standards that have to be met before we can pump this gas, pressurize it, and put it into a transmission pipeline for transportation. And so what you're looking at here, this equipment here, that's $20 million right there. This is part of it. You can get an idea of how precision this is. This is the best plumbing I've ever seen, actually. It's just remarkable. But there's a cost here. And fortunately, there is a huge co-benefit that we had no idea how big this co-benefit was going to be. The researcher from this campus who actually led us through evaluating this process is Donald Blake, and professor of chemistry. Donald has done, with graduate students from UC Irvine, measurements before and after the UC system went in and improved the leaks in the collection system. We're still making improvements in the collection system. So we don't know yet what the total benefit to the environment is going to be from less methane now going into the atmosphere because of our project. It's going to be substantial. It'd be premature to say how much, but it's going to be substantial. This could be a game changer. We're in the service territory of Southern California Gas. Their CEO about a year and a half ago announced this goal. They have adopted a public commitment to become the cleanest natural gas utility in North America. Their ultimate goal is to totally decarbonize their entire gas utility by 2045, starting out with this goal here. You see a 20% natural gas being renewed with being replaced by renewable gas by 2030. This will not just be from biogas sources, such as the ones you see here listed at the bottom of this announcement. It will also be some hydrogen. And you can count on UC Irvine being involved in a lot of the applied research and demonstration that needs to be done to achieve this goal. We're going to have a carbon capture symposium on campus. It was actually scheduled in June. We had to move it back because of pandemic. It will probably be rescheduled in September. We have these researchers lined up already. These are faculty, or in one case, president of a young company in Baltimore, who have technologies which we believe are ready to scale up. And a campus that has a cogeneration plant is the ideal site, demonstration site, to scale up something that isn't ready for a big utility infrastructure, but this is what a university can really do, is provide the demonstration site, scaling up opportunity. And by the way, this list isn't complete. I just met another professor from UC Davis who will be added to this conference. Anybody who's interested, let me know. You will be invited. Now, going back to this strategy again, I want to reemphasize one point, which is we had the premise going into this that decarbonized energy would cost more. And so the financial side of this was just as important as the technical concept that we laid out in this prospectus back in 2011 when this thing was completed. So this is a picture of our East Campus. What you see here is a bunch of phases of the East Campus housing. Many of you are familiar with it. That has been built, financed, designed, and operated by a third party, by American Campus Communities. That means it's not on our balance sheet. What does this have to do with energy? Well, what that means is it didn't affect our capacity to borrow all that we've had to borrow to do all of the energy efficiency retrofits that we've done on this campus. We borrowed more than $50 million using bonds that will be paid off in 15 years. Some campuses can't do that because they're at their debt capacity limit. So even a strategy like this, doing third-party housing, taking this kind of asset off of our balance sheet and off of our debt capacity numbers, makes it feasible to do that part of our plan, the financial feasibility part. Now in new buildings, we don't get any more money than any other campus to build a particular type of building. To do
Wendell, you have 2 minutes left.
To do exemplary energy efficiency and also a number of other life cycle things you see here on the right-hand side of this chart requires deciding not to do other things in the building design. And so this list on the left-hand side, I won't go through it, but again, it's available to you. These are all things we don't do anymore in buildings in order to afford the 15% of additional costs that it takes to build exemplary energy efficiency and life cycle performance in the buildings. This is how we're paying for it for our new buildings. So, reflecting on the whole thing, not just one big challenging goal, but aggressive sub-goals. Technology has been important, attitude's been equally important. Questioning all the status quo design practices has been important. Targeted energy, yes, it was built into building systems. We've pretty much discovered that. Then we made this explicit set of trade-offs that I just showed you to fund all these life cycle performance features in new buildings. And we assumed all along decarbonized energy might cost twice as much. Well, guess what? The first 15-year debt that we took out for our first big phase of energy efficiency was in 2009. That means that debt is totally paid off in 2024, 1 year ahead of when we have to start absorbing the additional cost of decarbonized gas. So that is how the plan fits together. Now, the final piece here, which I was asked to talk about, we've gotten a lot of recognition. I'll just show you this list here. I'm not going to go through all this. We don't have time. Top of the list, though, we're proud to be recognized by Sierra. Sierra Club has listed us in the top 10 for 10 consecutive years. 4 of those 10 years, including the current year, we're ranked #1 in the United States. The California Governor's Award, that is the highest environmental award in California. UC Irvine didn't win it just once, we won it twice, 2008 and 2013. I'll just pick one more out of here. President Obama's Better Buildings Challenge. That had a goal of 2020 to achieve 20% energy efficiency improvement for the whole campus. We met that goal 7 years early, the first in the country. President Obama himself recognized us for meeting that goal. He said, UC Irvine is ahead of the curve. So if you're an anteater, this is why we get the kind of recognition. It's because of these kinds of awards and accomplishments. And so you can be proud of this list of accomplishments. You've probably all played some role in every one of these awards.
Thank you, Wendell, for an outstanding talk. Since we are out of time, I won't be able to entertain questions at this time. And so what we will do is the following. For some of the audience, if you have a question, please send to us. We can forward the question to the speaker. Then when we post all the presentation material on the website, we will have the Q&A session to answer your question in that way when we are running out of time in this case. Wendell, thank you again for your outstanding talk.
Thank you.
So the next speaker is Michael Crawford. Michael is CalPlug Technical Director with a background in consumer electronic and power system design and construction of the high-low power supply and power management system and so on. So he has been one of the key contributors at the UCI's CalPlug Center. So Mike, take it away.
Thank you very much. Is my screen visible on your side? Is my presentation visible? GP?
Yes.
Okay, fantastic. Thank you very much, everyone. Happy Earth Day, and I know it's a tough time for everyone. Thank you very much for spending your time with us and joining us on the second day of our talk series. Today, I'm going to talk a little bit about plug loads and user behavior and how all this connects together, looking forward in California through 2030. This is going to be a three-part presentation. The first one, I'm going to go a little bit over an apropos topic of COVID-19 and what the impact of this is. The second, I'm going to look at California's GHG strategy and some ways to look at plug loads and consider modeling them in light of GHG. And then finally, some application bounds for battery storage. So as a quick update on what's going on out there is the United States Energy Information Agency released a report on April 7th, updating the targets for 2020 in light of COVID-19. So we're expected to accelerate GHG reduction by 7.5% this year. Last year was 2.7. Unfortunately, this is largely due to economic contraction and mild weather rather than organic changes that we made. And also, accordingly, electrical energy generation will be affected by 3% from decreased demand. Again, not organic effect of this process. And from this, the commercial and industrial sectors will be hardest hit, while residential is less. And of course, this is because people are staying home and not working. Likewise, renewables will be increasing while coal is decreasing, while natural gas is slightly positive. This looks great, but unfortunately, this is a reduced target for renewables. So this is a lesser number than was originally projected. Okay, so to take a look specifically at California, there has been a substantial reduction in energy compared to a year before. So at the midday peak generation, we're talking 16.2%. In fact, this is consistent with Italy as well. I believe is 15% total generation day over day average. This is a week's average, hour by hour put together. What's interesting is if you look at, there we go. If you look at the tail and the head of the duck, you'll notice the ramping has changed too. So in addition to having more generation during the middle of the day, the ramp up is slowed down in this current time compared to the same week last year. And part of this is because instead of everyone rushing to get ready in the morning and rushing to come home and then doing everything, the rate of work being done has been moved earlier in the day and a little bit later in the day. So the curve in some ways has been flattened here. This has an impact on the peak, not just necessarily the magnitude, but the shape of the peak as well. So as a consummate scientist, I have to look at myself, or always look at myself, and unfortunately my wife is involved with this. So a quick individual study, and I know David yesterday from LADWP put some interesting points in on this. I wanted to draw out some of these specifics for plug loads from my own observations. So keeping track of myself and our family's usage of stuff and using my sense monitor going back a year for my energy usage from last year and then currently this year, there was a substantial screen increase. So PCs, televisions, mobile devices. This is greatly increased, and I'll talk a little bit more about this in a general sense. Also, power tool increase. Many people are doing work at home, are doing taking work from from their work site and bringing it home to work on. So increase in devices being used. I also, at the beginning of this, purchased an extra freezer. Now, this is not just me. There's a number of others out there. In fact, in Italy, home devices has exploded for the market. There's been a large increase in kitchen devices and filters as well. So 8% in the United States right now since the beginning of this period. Cooking at home, I unfortunately still have gas appliances. So gas, I didn't present this, but gas has increased. Electric cookers as well. And water, because having to go out and purchase water is always a risky thing. I have a distiller and I've been using this. In fact, sounds a little kooky, but water filtration and water and air filters have increased as well. So even though I'm distilling my own water, there's a lot of others out there doing very similar to this. Kitchen appliances have increased, food storage and prep devices as well. There's less daily structure in general. Dinner is earlier in the day for us and less rushed with tasks. This is what we showed on the previous curve. Increased clothes washing. This is something also LADWP mentioned, and also because of the cooler weather and the rains, space heating has increased. Unfortunately, there's been one factor that has made this a little bit harder. My daughter was born this year, so carrying year to year, there's a little bit of a consideration there for the kid factor. If you look at the pattern of the graph, you'll see the structure of the day has dropped out, whereas it's very easy to look at the pattern of what's happening during the evenings. This is broken down now in the current year, and also overnight EV charging has dropped off on my side. It's much less there. So any kind of transportation electrification and charging at home has dropped off as a point. So these are some impacts on the residential side. Screen time increase is actually consistent with other localized disasters. Nielsen reports between 7 and 47% based on demographics. Whether in fact, because young people were watching TV less, that demographic has increased substantially. But this is actually consistent with other localized disasters during hurricanes, earthquakes, and whatnot. So this is not unprecedented. Specific increase is largely offset by contraction. So although there is home increase in energy usage, this is offset by other things. So reduced EV usage. If transportation is electrified, this is reduced, reducing your total load. The peak usage is reduced, and also there's changes in the patterns of use. There's reduced operational hours on the commercial side. Standby loads are consistent though, so this is something to consider, how loads are shut down and what the impact of this is. There's a number of standby loads that, if not efficiently managed and not efficiently mothballed during this period, are still contributing. On the transportation side, there's reduced total driving miles. If this is electrified, that impacts electrical energy totals, but also there's vehicle substitution. I noticed this myself, where I'd be driving a car to pick up something quickly or to go to the post office or something like this. I'm substituting for a less energy intensive vehicle. So this is something also to consider. If there's two vehicles idle, why take the more energy intensive one unless there's a strong reason for it? On the medical side, there's a reductive in elective procedures. There's also an increase in specific aspects of COVID-19 treatment. This is ventilators, areas of wards that are being used to support this and the support equipment, but accordingly, this is being offset by other factors in there, and there's also a large overhead that LADWP mentioned yesterday. GHG reduction is large, so to conclude some of these points, GHG is largely reduced due to economic contraction. Dispatch renewable loads during this period are actually being used. So the reduction in demands means that the curtailment that's normally happening due to changes in the loads and peaking at certain periods of the day where there's instability and needing to ramp up the base loads to make sure that that's being covered is not as critical right now. So in fact, on some days we're net exporting. I believe yesterday was a net export. Now that's not uncommon this time of year because this is kind of our blessed season where we're over generating, but usually not to this magnitude. So this is happening right now. And also this is a shock to the system. So there's long and short-term effects that we have to look at. So as many have mentioned, connectivity and remote usage is there. But one thing is also panic buying, people buying equipment right now. The fact that California has Title 20 and other considerations to keep energy inefficient devices off the market during periods where there's short supply, reducing the total market towards inefficient devices that otherwise wouldn't have been purchased but may have been purchased because of lack of supply of the desired device now becomes less of an option. So this is something to consider. Okay, so now shifting gears to topics. To set up the stage for California and the 2030 goals for GHG, just to take a quick look at the 2019 EIA projections for energy usage. We've all seen from the Rosenfeld curve, the per capita energy usage is decreasing in California, and the US kind of lagging behind it, but following a similar trajectory. We now see EIA is projecting an increase in the early 2020s, and part of this is due to electrification impacts. And because of this impact, this is offsetting some of the reduction that's happening. So the net change in the downward direction for electricity growth is being offset to some degree. Now, projected efficiency gains are baked in there, and this is why this peak is starting to turn back as far as the growth rate, but it's still increasing because of this continued electrification and also economic changes. So many of the low-hanging fruit items are planned to be reduced, and accordingly, the impact of electrification is showing out accordingly. So now to go into California, the 2030 goals are very difficult to reach at the current point, in part because acceleration is required to reach these. In fact, here's a little chart I took from CARB and annotated here. From the AB 32 initiation in 2006 all the way up to when we actually met the 2020 target, which was actually several years early in 2017, the year-over-year rate was a reduction of 0.7%. But from 2020, where we are right now, even though we've met this goal, all the way to the 2030 target is 4% per year. This is almost 4.5% per year. So it is substantial to be able to reach this. And at our current rate, we're going to hit this almost 30 years too late. The electrical sector has actually done very well for reducing the total GHG emissions, but now because other sectors such as transportation, which is a major contribution to California GHG, is being brought over into the electric power side, many of the low-hanging fruit items are reduced. Now, to meet this, the CARB plan relies heavily on cap and trade carbon offsets. Chris mentioned this yesterday, and this is a point of contention as far as is this effective to do that, but that's a little bit out of scope for this discussion. Right now, we have to make sure that the work on the electrical energy side is able to offset some of these other lagging factors through continued GHG reduction measures. So to take a look at the curve, and just to make this very relatable to now, I took yesterday's curve and brought this across. So if we look at the ISO curve, so this is the independent system operator for California, and we take out the mixture of what's going on right now. Natural gas and imports are being reduced because of reduced demand and increased or consistent supply for solars and renewables at this period of time. If we take this across here, you can see during the daytime, this is solar, and accordingly, wind during the night. Each of these particular renewables and non-renewables have an associated carbon intensity that's associated with them. This table is compiled, this is actually sourced from the International Panel on Climate Change, Annex number 3 from 2014, which is a common source for this. Please note that these are median values. In fact, there's actually a large spread, and each of these have a spread that's associated with them. So these are reference values, but these are not necessarily the only values that exist. There is variance in here. Also for batteries, the energy that goes into the battery and the energy intensity of that, it has an added factor associated with the battery's storage conversion and storage capacity and embodied carbon from this. So anytime calculations for what the energy intensity per kilowatt hour is, you have to take in the blend of what the energy is being received at a current time and accordingly run it through from the percentages of the blend through these factors, and you'll get out what the values are from this. So I've plotted this right now for two different utility groups. So this is a municipal utility is this first graph, and the other one is CalISO reported across here. So you can see that depending on the source, this particular municipal utility has a carbon source from coal, which does greatly impact what the amount of energy intensity is across the day. The CalISO one has less of an impact from this and accordingly is lower. What I did on here is I threw on my rates for my SDG&E plan for this example for winter. So there is a super off-peak period late in the evening, I'm sorry, early in the morning, an off-peak, an on-peak, and an off-peak. Now these values will increase in their difference during the summer. Right now during winter, they're relatively close. I want you to look at where the on-peak is for cost. So if we just take this into a binary, on-peak or off-peak, forget lumping off-peak and super off-peak together, we can see that the peak cost period is here. But if we look at this for carbon intensity, the peak carbon intensity is actually on a different point. So if I pop back and forth to these things, you can see that there's a relatively strong misalignment between these two factors. So cost lines up with demand and supplying of that demand, and the GHG is related to the generation capability from it. So they're not necessarily lined up to each other. So the question is, what are the impacts of carbon shifting versus reduction for a given device for load flexibility and the cost implications of this? So as we see it, there's two specific strategies to approach this. The first is conservation and efficiency, and this is going through and improving the efficiency of the device, reducing standby loads, improving the workflow of the device so that you're using it in a more efficient way. You're not waiting during certain acts and doing things that might be, if you have multiple devices, improving how they're being used in concert with each other. And finally, reducing the non-active workflow. So for example, this is leaving a device on, forgetting it's on, and accordingly having the device turned off. The alternative to this approach is using load shifting. So in this case, you're saving energy, and accordingly, if you're saving energy, you're saving carbon. In this case, you're actually shifting it from low periods, I'm sorry, for high periods of carbon to low periods of carbon. So this is an indirect and this is a direct method for GHG reduction. So how do these methods balance out for each other? So in fact, there's a relationship that can be made from these. This is a model that I presented, a very simplistic model here. Here are the constraints for the model, and accordingly, to do a daily energy reduction of 1%, so this is just 1% boost in energy efficiency, energy conservation, would require 3% in shift from a low period to a high period, and accordingly would have a penalty because of the cost misalignment of 8 cents. This is on a daily basis for a 1 kilowatt load. But if you want to do 10%, you need to shift almost 28% of that load across, and you'll have a penalty associated with this. Now, I did this in a very simplistic model here that is analytically calculated, but the PLSim program that we have, our tool that we've developed for simulations, will actually do this with arbitrary schedules in the new release. But so one of the questions I want to ask here is, how, for pluggable devices, how can we take 28% and shift it for that? Could you shift 28% of your television viewing? Could you tell a user to do that? How practical is this? So this is something to consider if you're trying to target energy reduction versus energy shifting as a means to do this. Now, I also want to drive out this point that if you have very close GHG intensities at different periods, you'll get diminishing returns with this. So if you're trying to move this to something where they're very tight between each other, you're going to have a very, very large period of time you're going to have to shift to get the equivalency out of it. Also, right now, GHG assessments and metrics are limited as far as they're being considered for utility programs. Right now, the California work papers look at the peak impact and they look at the total yearly consumption, but there's no standard metric for GHG. Such an approach here might be something to consider to drive forward to show why a particular strategy is justified, why targeting shifting energy versus total energy reduction is an approach to move forward, and then accordingly what the energy penalty might be from this due to the current cost structure. So let's talk about several loads here and what the impacts are on this. So first of all, I want to drive out, what is the flexibility of a load? For example, user preference. Let's just say I was watching TV and somebody said I needed to stop working, change my habits around to do this. Is somebody going to preferentially allow this to happen? Will the process allow it? If you need to heat a pool for a party or something like this, you have to get it done at a specific time. If you heat it and then you stop heating, it's going to be cold by that time. Is the process even going to allow it? What's the stability of the solution? If you put it together, is this solution going to shut down? Is the connectivity solution there? Is this too difficult for the user to maintain? And finally, is there financial incentive or price impact? Is there an incentive to drive it from the utility or state side? Is the price impact either driving it forward or working against it? So let's talk about a couple residential plug loads and what the impact is. So I just chose 3 here that draw out some major points. For example, a refrigerator. For shifting the load, you can't really do a lot with the temperature setting, but you can do a little bit of pre-cooling at certain times, and you can change the defrost cycle. You can move the defrost cycle around. On the EEEC side, you can have user alerts and encouragement. You can change the device improvement as far as the installation and the mechanical improvement. One thing that's kind of interesting is on my side, my refrigerator has an alert that tells me if the door is open or cracked. Sometimes I miss it, and that little beeper has saved me leaving it open all day. So this user interface, this behavioral interface, is not necessarily a load shift, but does have a great carbon impact. So keep that in mind. From the earlier example I made about televisions, shifted loads are a consideration here too, as far as what's the possibility. Users really don't like that, so that's really a concern here. Same thing with PCs as well, or computers. But there are strategies on the EEEC side that can save carbon, like reduction of active and standby loads. Tier 2 APS has shown this, that you can save up to 50% and greater using this approach. And finally, water heating. This is actually a hybrid overlap where using triggered set point and hysteresis band adjustment can do this. Accordingly, some of these carry between the two as far as effects. So sometimes targeting EE and EC can actually draw in when you add another factor in for timing. So not just what the user is doing, the on-demand, but adding in a factor for timing and accordingly tying all these together. So a quick conclusion of this is there's a misalignment between several of the factors with energy reduction and cost of energy reduction. Accordingly, GHG reduction is affected from this, and the metrics of GHG reduction have to be considered accordingly and what the impact of these components are. I'm going to go kind of quickly here due to time restrictions. One of the things are residential small plug loads. We put a report together for San Diego Gas and Electric, and I'd like to also point you to Fraunhofer and CTA's 2015 Connected Devices report. There are some challenges with connectivity to enable additional capabilities for energy savings in small devices. Now, this is not said that these devices can't act in a coordinated fashion to help manage a greater system, but individually, plug load devices, small plug loads, often can be managed better by ad hoc controls, individual controls rather than coordinated. But that's not to say that these sensors can't enable other devices to work better. There are still many EEEC opportunities out there for residential plug loads. But one thing I want to draw you to is the commercial side. On the commercial side, it's workflow driven, it's clear process and policy, and there's clearer, usually, ownership and responsibility of devices. There's consistent device management, but also there's gap considerations. There's devices that are shared use devices, and we've looked at these, including water coolers, coffee machines, printers, these devices that may or may not have energy management that's effective for their current use. These are targets, and doing coordinated connected energy management and time controls do have opportunities that really should be explored. As a last topic to draw in, I'd like to talk a little bit about battery storage. So one of the things we've been looking at is what is the scope for battery storage? What are the approaches that are feasible here? Oftentimes, solar overproduction outside the scope of net metering is a consideration. Also, islanded microgrid. This was something that was brought up during the wildfires in California, where people's solar systems are not able to supply their current structures. They're only made to feed back as a net power providing, but they can't do it as backup. So what could be done for backup or backup for garage doors? And also peak load reduction. Can you use batteries to balance off peaks, and is there a financial incentive to do this? For scope, are we talking a whole house? Are we talking about a dedicated power bus breaker? Are we talking about a scalable circuit? Are we talking about something that can individually select devices within a set, or devices that can turn themselves off or on to manage their energy usage over a circuit in this particular condition where this battery is supplying it? Also, what is the scale, cost, and installability of this device? So are we talking from the lowest end, a computer UPS, your little box that you plug into your computer into, so when the power goes out, you can use it a little bit more? Are we talking about a Tesla Powerwall that has to be installed by a specialized technician at a high cost? And even vehicle to grid systems. which are mid-cost, high capacity, but maybe a semi-free ride due to the availability of the device. And accordingly, also in these considerations for efficiency and transfer rate, how do these weigh in there? And are there strategies with intelligent waveform, frequency, and control outputs to help boost the capability of controlling certain devices for extended runtime? And also, what is the consumable and device longevity? So considering these factors and weighing this out, when you look at a whole home battery compared to this single device battery, you can see that this optimization is a question of balance. Where can you shift this and what is feasible? So to show just, one example here, a single circuit device battery is feasible with a 3 to 5 year payback period, assuming a 50%, this is 50% of the lifetime. So we're talking 6 to 10 years for the lifetime for a 1 to 2 kilowatt hour user replaceable battery. So this is a kit that's installed rather than an electrician. It goes into a disconnect box on an HVAC or can plug in near the electric meter or even into a 240 socket. Breakers may be changed under certain conditions. Basically, such a device is feasible, but if you're trying to split the difference between the peak rate and the lower rate, this does not necessarily have a GHG impact. In fact, it could have a negative GHG impact, but if you're charging from the individual solar being produced, this would have a positive impact on GHG. Remember, this is highly dependent on several factors that are associated with the setup, including the charge rate, the displaced energy from here, and according the cell cost and the system cost. But there are many other optimization points here, and this is something still to continue to explore. So a quick summary of the points that I brought up. There's shocks to the system that have occurred because of COVID-19. Right now, we've seen short-term impacts on plug loads, but the long-term, whether our economy is going to a more remote application, whether this changes the PC markets or more desktop machines, more large monitors are in there, this is still to be seen. There's still questions to be asked here. But one of the things that is interesting is we've seen that new devices are purchased in a panic. Having a stock of high quality, energy efficient, and well pre-configured devices is important to ensure that during these panic buy times, devices are favoring early and continued efficient use. Major work is required in California to reach the 2030 goals, and some of the work that the energy sector for electricity has done has been offset by electrification, so there's still more work to do there. There's metrics that still need to be developed and improved for GHG focus in utility programs, codes and standards, and best practices for plug loads. EC and EE can provide complementary roles to load shifting for GHG reduction, but flexibility always has to be considered. This is one of the major points there. Different plug load devices, residential and commercial, have different usage requirements. Sometimes looking at one may not give conclusions about the other, so looking at both sides are important. On the SDG&E report that we prepared, we looked at connected devices for residential applications. We found some concerns with the capability of solutions, but that doesn't necessarily translate over to commercial. And finally, there are many applications for home battery systems that could have commercial feasibility, and there's a continuum here with many optimization points for this feasibility. It's something to still continue to look at for different applications. So I'd like to thank everyone for your time for this presentation.
Mike, thank you for an outstanding presentation. Now is the Q&A session, and I have a short question. What is your view about the centralized versus distributed energy storage for either commercial or residential usage?
That's a very good question. One of the things that I didn't point out earlier on the commercials on the chart with California's energy usages, the battery applications are actually being used to smooth out, the commercial battery applications are being used to smooth out intraday peaks for solar and for wind. So it's not just necessarily peak production. So there are very tight coordinated capabilities that are available for the commercial side. On the residential side, to get that same kind of capability would require an extended system, which is not really in place right now, extended capability. But at the same time, we've seen that islanding solar that comes from a grid does have the capability of providing power backup and meeting other goals. So there are pros and cons, and of course on the utility side there's an economy of scale consideration, but on the other side there's power backup and other concerns. But one of the challenges is always, okay, so the device is installed, when it has to get replaced or if it has to live for its entire lifetime, is there an incentive to maintain that system? Is there a financial incentive? And this is one of the challenges on the residential side.
Thank you, Mike. Thank you again for your outstanding presentation. And we are going to move on to the next one. The next presenter is Arden Donnelly. She has been having gathered together an emission reduction credit, or ERC, buyer group. Arden developed and executed the world's first major forward ERC purchase agreement to finance carbon sequestration in agriculture soil, as well as the first ERC sales finance carbon capture and storage project. She has been a small business developer and consultant for over 40 years. Arden, please take away.
First of all, I'm not going to spend a lot of time describing NORI and what we do. I hope everybody feels inclined to go check out our website. And anybody who'd like to discuss NORI more, please feel free to email me at any time. And there are and you'll see on the first page of my slide deck the contact information for that. And I'm sorry, you guys, I'm yet another one of these dense slide presenters, and it's not my goal that you read everything on the slides as we're going through this presentation this morning, but I just wanted to make sure that you could see that the data that I'm referring to are here, and encourage you to download the slide deck later when it's made available at the website. Wanted to start by giving us context. Getting to 2030, according to the UNFCCC, if all of the nations that have signed commitments under the Paris Agreement keep their commitments, we still need to draw down or offset an additional 15 billion tons per year of emissions, and be doing that and maintaining that by 2030 to maintain a cap on warming at 2 degrees in the year 2100. In other words, if everybody keeps their current Paris process commitments, we're still going to miss a 2-degree warming cap goal significantly. And as you know, when greenhouse gases are discharged into the atmosphere, some of them have very, very large lifetimes. So what we've discharged by 2030 has a big, big impact on the world we might be living in 2100. So if everybody does everything they say they're going to do, we're going to be 15 billion tons a year short. To put that in context, total greenhouse gas emissions discharged by energy and industrial sources and energy use, so not counting any natural variations, run 37 to 38 billion a year. So that's a big miss. I'm going to show you some numbers that come out of this the Carbon Majors database report from CDP, the Carbon Disclosure Project. I just want to say before I go through the numbers, I picked this report because the numbers in this report are the smallest emission estimates you will find for the companies reported anywhere. So if you one day have nothing to do, which is not the case for any of us, I know, if you maybe just compared the 2015 Scope 1 and Scope 2 emissions estimates in this report to those in the company's own sustainability reports, you'll typically find that the corporate reports have higher emission estimates than you see in this report. So when I use this report to do some number crunching for you, I'm using conservative estimates of corporate emissions. I'll go past this, but just so you can see, in that report, this shows you a listing and Scope 1 and 3 emission reporting estimates for the top 50 corporate emitters in the world. Bottom line is 50 companies account for 70% of that 37 to 38 billion tons that goes out every year. Only 50 companies. 28 of them are state-owned and controlled directly, and 22 of them are technically privately held or publicly traded. But of those other 22, 8 are still state-controlled. And if all of these companies were to release only their proved oil and gas and coal reserves that have a value on their balance sheet, that would amount to 110 to 140 gigatons of additional CO2 being released to the atmosphere. And that's only their proved. So they have unproved reserves also on their balance sheet. I'm saying assume we write those off. And if you go to the 22 privately held or publicly traded, that's 700 to 800 gigatons. To put that in context, World Resources Institute says we can't put that much up in the atmosphere and get anywhere near a 1.5 degree to 2 degree cap. So no matter what anybody says, if these 50 companies do not massively reduce their emissions, the emissions their customers release when they are using the products they sell, there's no chance we're getting anywhere near any of our targets anytime soon. These 50 companies are 57% of the whole global greenhouse gas inventory. So what are those 50 companies saying they're doing? I picked, for those, they don't all have sustainability reports or climate plans, but I picked Equinor, which used to be called Statoil, controlled by the government of Norway, because it's seen to be by many to be a good guy out there and does have one of the most aggressive in green terms asset management plans as reflected in their financial reports and their sustainability reports. And you will see that even when we're talking about Statoil, while they have reduced scope 1, the emissions in their own operations, their reduction of their emissions in their own operations were 1/26 of the increases in the greenhouse gases discharged by the consumers they sell to between 2014 and 2018. And you will see that in every single corporate report, any commitment to what they call new energy or green energy or alternative fuels, at least to date, is financed by more sales of the fossil fuel products to the general population. In every report that I could see for, not all the companies listed publicly report, up until and including last year, even companies that have reported what sound like aggressive sustainability goals are still dedicating at least 50% of their capital spending to developing oil and gas reserves, exploration and development. And even in this case, you can read the details on your own. You can see that even when we're talking about Norway's Equinor, we're not getting anywhere near corporate commitments that would get us anywhere near our reduction goals. So this is reality. And I think I want to underline the fact that 36 of these companies are controlled by governments, many of whom have made commitments, and these governments are making those commitments for everybody but the companies they own, and the companies they own all have plans to continue increasing their scope 1 and scope 2 combined scope 3 combined greenhouse gas emissions through 2040. So what does that mean? I'm not arguing offsets are the end all and be all. I think we should be taking the numbers seriously and stepping back and asking ourselves, what do we do to mobilize a sincere commitment to reducing global greenhouse gas emissions, not just my household? But we're also out of time. So any commitment to capping warming has to include a plan B, not plan B instead of plan A, a plan B on top of plan A. And we would argue that the world's food and fiber producers have the capacity to draw down and sequester significant amounts of heat trapping gases out of the atmosphere while increasing soil health and productivity in so doing. So investments in those projects that are storing more carbon in topsoil and root systems, where we're in those fields we're relying on for food and clothing, are a rational first choice for next investment. What's the potential there? And if you compare the numbers I give you on this slide to estimates from a lot of other sources, again, I'm intentionally being conservative here. But the soil science community agrees, there is a consensus that the soil organic carbon stock in our topsoils, and this is for all land, not just cropland and grazing land, is about 50% what that stock was 300 years ago before we introduced intensive food and fiber production practices. And that the minimum potential for us to draw carbon into the topsoils is be getting us back to what we know to be that 300-year ago stock level. There are many things I really like about this story, including just noting who the 10 countries are that are sitting on 60% of that carbon stock, which is CO2 drawdown potential, because there's not a perfect but a nice overlap between the countries that have the potential to be part of the solution and where the emissions are either large, are large as a proportion of total global anthropogenic emissions, or growing, or both. If we were, again, applying a very conservative standard, and I'll quickly say what this standard is, if we applied a very conservative standard and gave ourselves 100 years to rebuild the carbon stocks in our croplands, forests, and grazing lands to what we know they were 300 years ago. So I'm saying let's build it back up 3 times faster than we took to break it down. And when I say I'm being really conservative is for any given field, it will only take, depending on its status, 10 to 30 years to rebuild its carbon stocks back up to what we call saturation level. So when I'm saying we're taking 100 years to get all of our carbon stocks back to saturation level, I'm phasing in the fields. I'm not starting every field in every country right on day one, but saying how fast do I have to get the fields phased in to get this whole thing done in 100 years. If we take 100 years to rebuild those carbon stocks and we don't need new technology, we know how to do it now, that's 10 to 25 billion tons CO2 equivalent we can be drawing down every year between now and 2030, potentially covering off that deficit, that 15 billion ton per year deficit that I mentioned earlier. Why does this make sense from many directions? The changes in practice on the land that we implement that draws down and sequesters carbon also increase soil health, increase moisture retention, make our soils more resilient, and therefore improve their ability to produce food and fiber in the event of warming while they're mitigating the warming threat. That's the first thing. The second thing is, and I will go back to this, at carbon prices of $35 to $40 a ton, we're living in a world where carbon prices are more like 10 to 15 right now. The carbon prices of $35 to $40 a ton, US, Canadian, and worldwide food and fiber producers can more than adequately finance the full costs of achieving this ecosystem service for the rest of society. And if you're going to spend money on a mitigation action, why don't you send it to the people that are growing the food and the fiber, the food you eat and the fiber you wear? I wanted to give you some specific numbers. On this slide, I'm saying that if we just look at US cropland acres, so I'm not counting grazing, managed grasslands, grazing lands, or forests, and I'm not sequestering carbon by converting any food or fiber producing land to forests. It's staying in this scenario in food and fiber production. If we start moving US croplands towards regenerative practices at a reasonable, as in slow, conservative rate, the US croplands have the capacity to, over time, offset the lion's share of the gas-fired electricity emissions in the Energy Information Agency's lowest petroleum price scenarios. If we add in managed grasslands, forest lands, and other US crop and fiber producers and forest operators can offset not quite, but almost 100% of US greenhouse gas emissions. Now, I'm not arguing offset instead of reduce. I'm arguing both. I just think the numbers show you very clearly that our best efforts to achieve our goals with reduction are not getting us anywhere near where we need to be, and we are running out of time. I'm saying this is a really optimistic scenario. You've the capacity to deliver new revenues from new sources to food producers on whom the nation depends, and to get us back on track to capping warming at 2 degrees by 2030, only if you do this. So it's almost crazy not to. I want to stop for a second because I want to say something controversial, and hope that you react with lots of questions and interaction. But when you go back to that list of companies, anybody who's interested, I encourage everybody to do their own little exercise, particularly with this list, for any company for whom you can find a published financial report. This is something that I've been doing every year since about 1999. Assume that you had an unlimited amount of money and you went and you offered the shareholders of these companies, you offered to buy them for 1.5 times the highest value their shares traded at over the last 12 months. And you write down what that cost you. Then you write down what it would cost you to retire, so fully pay out all of the company's long-term debt. Take any resources the company set aside to reclaim contaminated sites and multiply that number by 4. Add that number to the numbers you've written down. Assume you're going to lay off 50% of the payroll, but you're going to lay them off at full pension regardless of age. Write down that cost. Add up those costs and take and divide them by whatever you think is a reasonable amortization period, 10 years, 20 years. Divide those costs by 20 years of scope 1+3 emissions for the company that you just bought. And I'm not arguing that we should be running around with public resources buying and shutting down companies. I'm arguing that the number that you're looking at after you do that calculation is your reference carbon price. It's any good policy, any combination of good policies, if they're efficient, should be efficient at an effective carbon price that is equal to or less than what it would cost the taxpayers to expropriate and compensate the owners and lenders, owners of and lenders to these companies. So I'm not saying, don't get me wrong, I'm not saying do it, I'm saying there's a reference price. And when we're advocating for policies and strategies that don't work at that reference price or need the carbon price to be 4 or 5 times that reference price, maybe we're talking about inefficient policies. So I'd ask more people to start doing that analysis so we could fight over what the real reference price is and how to maybe integrate knowledge of that reference price in our policy discussions. working with those numbers made me switch from being probably one of the most aggressive advocates for cap and trade type regulation in the world to someone who actually is not a supporter of cap and trade, or at least beyond outside the boundaries of an individual state or province. And there are a number of reasons for that, but I will just say that I've formed some personal opinions about what efficient regulation looks like once I started to have to just make my theories work within that constraint of that reference price I just walked you through. And I'd sure love to be debating those questions in that kind of a context with more brilliant people like all of you guys. And really, if anybody's interested, we really encourage anybody to email and start a conversation. I've formed a strong opinion now that the right regulatory context is one that basically works exactly the way we got ozone depleting substances out of the refrigerant supply chain, the way we got lead out of gasoline and sulfur out of diesel. We don't allocate tradable entitlements to emit to end users and distributors of fossil fuel intensive products and services, which is the cap and trade story. What we do is we say if you supply any form of energy project, you report your fossil carbon content per million BTU or gigajoules of delivered energy. So this looks a lot like a low carbon fuel standard, just simplified. And the supplier is obliged to report and reduce that fossil carbon content over time, can trade over compliance credits. And in that world, I see 3 and only 3 necessary offset or alternative compliance options. I guess what I'm saying is maybe the way to get fossil carbon out of our supply chain is to order the suppliers to reduce the fossil carbon in our supply chain. To quantify progress in sequestering carbon in croplands and grazing lands, we are working with Comet Farm, which is out of Colorado State University. We are talking to and working with other potential analysis groups. We're really proud of our quantification and verification methodology of our science peer review committee. And again, would love anybody and everybody who's interested to go to our website, try to get a handle on what we're doing, and email and engage me in conversation if you're at all interested. Maybe I'll stop there and go to questions. Is that okay?
Thank you for excellent presentation. I do have a question from the audience. The question asks, if only 250 companies are responsible for 70% of anthropogenic GHG charge, it seems rather insignificant. If I am avoiding trip with my fossil power car and flight. So do you think that collective individual action will make any dent given those numbers?
I hate to say this to you. My answer is you're correct. Focusing on individual, personal, and household choice is the reason we haven't made very much ground for the 30 years I've been working on this file. Whoever asked the question, what I have to say to you is, I've been working on this file for 30 years. I only realized that 3 years ago. So if you've been working on the file for like 5 years and you realized it now, what does that make you 6 times smarter than me? The concept that the end use consumer has control of our supply chain is a misperception. And when we wanted to get the lead out of gasoline, we didn't cap lead emissions. We didn't put lead ratings on cars. We didn't put a premium price on leaded gasoline. We said, You supply gasoline, you report your lead content, and it goes down. And you can trade lead content rights with other suppliers. Every time we've been serious, we regulated what could be sold to us.
Thank you. I have a question for you. You talk about soil organic carbon stock growth. What, from technology point of view, what is the major challenging there because of the labor cost, or what is the major challenge? Can technology be of help?
Yes, there are two challenges in terms of a shifting from intensive and traditional to what we used to call conservation and sustainable and is now called regenerative food and fiber production processes. There is always a significant upfront equipment cost, and there is usually a labor cost increase, which I'm okay with because more labor, more jobs is not a bad thing from my perspective. If if everybody makes the right choices, and that's difficult because the right choices are different choices in different locations. If everybody makes the right choices, it's reasonable to forecast a 7 to 12 year payback on those investments. So if you can start that transition started and carry the food or fiber producer through to year 7 to 12 after an effective transition execution, they will be more profitable and productive and probably not abandon the more sustainable practices no matter what, because they are getting a better return. The transition, though, tends to be financially very, very stressful between years 3 and 5 or 6. I see 50% of well-intended adopters bail in that period. So when we're designing a market, it's very sensitive to the fact that a couple of things are true. 7 to 12 year payback is pretty good looking to an electric utility. Most food and fiber producers don't have enough capital bandwidth to tolerate paybacks that long. And if we design a market that can draw those for whom 7 to 12 years is a reasonable payback in as financiers, while creating diversity of revenues for food and fiber producers, while everyone involved knows that the tough years are years 3, 5, and 6. And so how do we build a market that's sensitive to that and there to hold it up during those early years? I think we can do it.
Yeah, thank you, thank you. I have one more question from audience. What is the current impact and expected future impact of desertification of a wiregrass land, US or worldwide?
I want you to send me that question because I don't think what I was going to say out loud is necessarily the right answer. And the reason I say that is because I'm finding that if I give you an answer that's 2 or 3 years old these days, it's the wrong answer. And I haven't looked into that for a couple of years. Put that on my question list. I'll respond to that.
Thank you. Thank you. So it seems to me there is no more question at this time. I want to thank Auden for the excellent presentation, and we will move on to the next presenter. Thank you. So the next presenter is Michael Mitchell. Is our special keynote speaker who has been a leader in green initiative throughout his career, from work in the early 1970s planning the first residential community with a fully recycled gray water system to current work on self-sustaining community in Europe and China. He was one of the very first organizers of the first Earth Day in 1970, 50 years ago. Michael, please take away.
Thank you. Hopefully I'm doing this right, sharing my screen.
Yes.
Yep. Are we there?
Yeah, one more click. Yeah, excellent.
Okay, excellent. Well, it's a pleasure to be with you here today. Obviously, an important celebration, 50 years. For those of you who didn't experience the 1960s, I'd like to kind of take you through what forces and dynamics brought about Earth Day. And then I was asked by the organizers to discuss kind of where we are now from my perspective and what another 50 years will look like. Hopefully many of you in the audience will experience that. Am I not sharing my webcam? Okay, where we were. One of the things I think a lot of people miss is understanding how long we've had an understanding of global warming. Over 125 years, we've understood this effect. I actually think the old, it was called originally hotbed effect. I think that's actually a more appropriate name. But California played a very important role in the 1950s, 1960s, from Caltech, and of course in San Diego at the Scripps Institute. And so we had established scientifically by the 60s a very clear understanding of these forces. See if I can. I don't know if any of you have seen this film. I saw it when it first played in 1958. It gives you some sense of the public was already being introduced to the idea of global warming, creating melting ice caps. Dr. Baxter ran that program. Very interesting films. And even Congress was quite well informed of these issues in the 60s. President Johnson gave a speech to Congress discussing the issues of burning fossil fuels. Here he is shaking hands with the Scripps scientist, Roger Revelle, who worked on those issues. Even the Petroleum Institute was well informed, the energy industry. In 1967, the American Petroleum Institute commissioned a study from Stanford Research Institute to look at the impact of fossil fuels on the environment. And as you can read here, their conclusions were quite stark. It talked about causing serious worldwide environmental changes. It could affect sea level rise, glacial melt, and have severe environmental damage. So those issues were well established by the 60s. And then for the general public, a great deal of literature was produced. Many of you are quite familiar with Silent Spring, which came out in 1962. The population bomb. For me, The Tragedy of Commons, if you haven't read it, Garrett Hardin's work, it's a must read. I think a very important work and influenced my own involvement. This image at Christmas Eve in '68 kind of changed our perception of the world. The little blue marble in space. It gave us a sense in the 60s of how small and precious our Earth really was. Coming up just before Earth Day, the Santa Barbara oil spill in '69 played a key role in actually bringing Earth Day apart. I'll explain that in a moment. And then many of you may be familiar with the Cleveland, Ohio fire. This is what some of our rivers actually looked like in that period. The river in Cleveland caught on fire. Paint companies, oil companies, various industries used to dump directly into our rivers. After World War II in the 50s and 60s, economic growth was paramount, and the environment wasn't taken into consideration. And this fire kind of shook the nation. Another part that led up to Earth Day were the anti-war teach-ins. In October 1969, the universities around America held a teach-in to end the war. And Senator Gaylord Nelson, who's the founder of Earth Day, as you all know, he had gone to the oil spill in Santa Barbara, and he was flying back from that, and he had read about the anti-war teach-in, and that gave him an idea to do an environmental teach-in. He had been trying to pass environmental legislation in the United States and not doing well. And he thought that he needed the support of the American people to kind of force Congress to pay attention to these issues. So in September 1969, he announced kind of an invitation for an environmental teach-in. Leading up in early 1970, students around the country, I would use the word angry. We were angry at the government and corporations for not paying attention to these issues. Here at San Jose State, they bought a new Ford in the middle of the campus, dug a ditch, put the Ford in it, and buried it as a protest for the whole issue of cars and creating pollution. It helped actually instigate the first environmental studies department in the country. That led up to Earth Day. Obviously, we're celebrating its 50th anniversary. At that time, 1 in 10 Americans participated. It was basically driven by college students, but the public in general obviously took part. Many of you know the Today Show. They actually devoted an entire week to the issue of Earth Day. You can see Hugh Downs here, who was the host of the Today Show, and he opened the week. This gives you some sense of the feeling of the time. Our Mother Earth is rotting with the residue of our good life. Our oceans are dying and our air is poisoned. Do we go on demanding more and more until we suffocate or die of plague or famine? So there was a great deal of dramatic interest in this topic. And that's, in a sense, what produced the original Earth Day. I wanted to give you a sense of the kind of attitude and feel. So now we'll move on to explore where we are post 1970. I'll do that rather quickly. Out of the kind of inspiration and political force of Earth Day, the EPA was formed. It was created 7 months after Earth Day in 1970. California Environmental Quality Act, the same year, was signed into law by Governor Reagan. You can see this rather amusing image here. The air in LA was incredibly dirty. It has been reduced now to just 80 days a year. And obviously CalPlug became an institution from that period. In 72, the Clean Air Water Act, 73, the Endangered Species Act. So there was this momentum from Earth Day that created these programs. even internationally. The Chinese, the United Nations Conference on the Environment, the first one took place in 1972, and China sent its representative. So there was a worldwide kind of response to Earth Day. Today, we have over 1 billion of us participating in some way. They say 193 countries actually participate. And again, today feels very much like it did in 1970. It has been driven by youth. Greta Thunberg's UN speech is very familiar to me, the kind of speeches that were given in 1970. And youth, once again, are kind of leading the charge. Again, I refer to China. Youth all over the world are taking active roles on environmental issues, which are all quite positive. So, given all of that momentum, the political kind of will that had been established, what progress did we make? Unfortunately, as you've been hearing through the day, not much in some areas. Global CO2 emissions since 1970 have increased 300%. You're all familiar with this graph about atmospheric CO2, and obviously CO2 in our ocean increased 30% since 1970. Global temperature on the rise as a result of these greenhouse gases. So, what's driving these changes? What didn't we fix? Basically, it's GDP. The global per capita increase in the United States been 250%. Global GDP in the world now since Earth Day is up 500%. And what's truly amazing is China's GDP has grown 5,000% since Earth Day, the first Earth Day. And this chart is critically important to understand the tie between GDP and energy consumption, and GDP and energy consumption and population growth. They're exactly equal. They're driven, each one, GDP is in a sense a direct byproduct of energy consumption and population growth. We're not going to do a lot about population growth. That's baked into the formula. But we obviously need to address this tie between GDP and energy consumption. So this is just a rephrasing of that. GDP, up until now, they have been tied 1-to-1. They're a direct relationship between converting primarily stored energy, stored sunshine, into applied energy, basically goods. So how did we do that? Since 1970, global vehicle production is up 300%, 200% in the US. Air travel, which is a heavy pollutant, has doubled every 15 years and projected to double again in 15 years. 1,400% increase since 1970. And the part that's interesting for someone my age, having lived through this, 1970 was a good life. We weren't deprived in the way we lived, but we obviously have increased our these various kinds of consumptions over time. Per capita world energy consumption is forecast to double over the next 50 years to 2070. And even though per capita energy consumption is somewhat down in the US, about 10% since 1970, which is an excellent accomplishment. And California contributed a great deal to that. The US demand is still forecast to increase by 2070. I'm sure you're all familiar with the UN's Climate Action Summit. Basically, the UN Secretary General said, to limit global warming, we're going to require unprecedented social and economic transformation. But the CO2 emissions is not the only environmental issue we're facing. Humanity has wiped out 60% of the mammals, birds, fish, and reptiles since 1970. Deforestation alone is a major contributor to global warming. Studies show that perhaps up to 40% of all of the carbon released into the atmosphere since the Industrial Revolution is a direct result of deforestation. And it alone has a baked in, if we continue our deforestation of our tropical rainforests, it'll increase 2.7 degrees Fahrenheit by 2100. We have cut down 800,000 square kilometers of the Amazon forest since 1970, and primarily for two reasons: cattle and production, food, soybean production, primary reasons. Obviously, today we're doing this not in person. We're all aware of this, of COVID. Our life has changed from it. COVID is obviously a symptom of us pushing the boundaries of our life and creating unnatural contacts with wildlife. SARS, MERS, H1N1, last 20 years, this is our fourth potential pandemic because of this destruction of the natural world. So, where are these trends leading us? The University of Massachusetts has a sustainability study center, and they did a study of 200 leading environmental scientists to get their kind of view on where we're heading. And the concern is that we have a number of small but overlapping environmental problems that in effect may cascade and become self-reinforcing and could potentially cause a systematic collapse. These are very troubling comments. So, Life on Earth 2070. I happen to be an optimist. So, this edition is this month's. Many of you may have seen it, the National Geographic. It's got a two-sided magazine. One side is How We Lost the Planet, the Pessimist's Guide to Life on Earth in 2070. The other, if you look at the other side, it's How We Saved the World, an optimist's guide for life 50 years from now. So, from my view, all we need to do to save the planet and our natural world is simply stop doing what we're currently doing. That may sound a little meaningless. I want to give you, if I may, a couple thought experiments. I think sometimes we can have we're all looking for solutions, and we hope that technology and increased efficiencies can be the solution. So these are a couple ways to kind of look at it again as a thought experiment. The question here, how much CO2 emissions can be reduced if we convert 2/3 of global energy production to renewables by 2070. The problem is global energy production is forecast to increase dramatically. It's supposed to double at least by 2070. So when you take all of that into consideration, even converting to primarily renewable energy production, we still only reduce the overall footprint about 10%. How much CO2 emissions can be reduced by going electric? Let's be optimistic and say we convert 2/3 of the world's vehicle fleet to electric. Unfortunately, the demand in the developing world is so great, we expect the fleet to increase 500% by 2070. So even if we go electric, we're going to produce about 250% more CO2 from our installed vehicles. What about airline travel? We talk about making GE talks about more efficient engines. Well, let's be incredibly optimistic and say that we increase efficiency 100%. Unfortunately, current air travel projections, the virus aside, because who knows what's going to happen in the next few years, but the demand curve that's being projected is a 400% increase. So even if we technologically can make 100% more efficient engines and airlines, we're going to increase our total output of CO2 200% in that sector. Global food production. Alden was talking about the issues of regenerative agriculture, which is, in my opinion, one of the key issues that we need to address. Absolutely important. So let's say that we can reduce global CO2 emissions in our food production program 50% by 2070. Unfortunately, we have to increase our total amount 25%. The world's population is expected to increase another 20%. So our net savings is somewhere in the 15 to 20% range. So the driver here is global GDP growth. It means increased applications of energy, basically consumption patterns. So as an optimist, how do we achieve the good life? I believe mankind is at a fork now in the road. This photo image, lovely as it is, has a positive bright side and a potential dark side. We can continue as we are, tying GDP growth to high energy and material consumption economy, or we can tie our GDP growth to kind of new ranges of values and experiences, which are much less material consumed. So let's imagine right now that we're having this conference in 2070, and we're looking back and we're saying, what did we do right? I would say we broke free from our destructive economic equations, equating GDP value, which right now is a direct one-to-one relationship to the CO2 discarded into our atmosphere and oceans. We have to break that particular formula. Obviously, resource attraction levels. Right now, GDP is an exact equivalent product of resource extraction. We've got to break that cycle. So I think looking back, we increased our GDP, but the contributing factors will change dramatically. One of them will generate a great deal of our global GDP by working on maintaining our stressed environments and rebuilding nature's resilience. Another thing we'll do, we're going to shift our global budget priorities. We need to create global resilience. We got to increase research. particularly materials research and applications. We need to prioritize lifelong education, health, and life extension. So much of the GDP would shift into growing into these areas. I think we shift our focus from meeting our needs, our stimulus and status needs, which basically that drive consumption, more through richer experiences than through material consumption. I think we're going to become more connected. We've just started that cycle in the kind of human mission here. Looking back, we have said we utilize the digital revolution, particularly 6G, which is going to be with us in about 10 years. It's going to give us abilities to explore digital, digital spaces, self-exploration, social interactive, and creative pursuits in an entirely different way than we are. And I think maybe a benefit of kind of cloud networks, we may break down the issues of these national barriers. We may have such easy access across barriers now that we're going to all feel like we live in a connected neighborhood. And I believe that will give rise to completely new ways of kind of understanding one another and cooperating. I think we'll have more nature. Global food production, I believe, will be less soil-based. I agree with Alden in that regenerative agriculture is going to play a very key role, but I also believe we need to return more of nature or more of land to a native natural state. So, and I believe we're also looking back, we'll changed our diets. Meat production is a primary consumer of water, land, and a number of other resources. It's not an efficient way to feed the world. And I think our world is going to be much more equitable. I think automation over these next 50 years will give us a much more bountiful world, and we will do it in a much more efficient and a much more with much less resources. So in 1970, we all knew this poster and laughed about it. We have met the enemy and he is us. And that is the issue, choosing which path we're going to take. It's really not about technical solutions. We have all of the knowledge we need right now. We have all the capabilities. It's more about us understanding choosing the right path, I would say. So thank you for listening, and hopefully it was of interest.
Thank you, Michael, for outstanding presentation. I love it. So now is the Q&A session. So for your presentation, you say the technology is already there, and it depends on how we use it, and to face this challenging of continued demanding of the growth of GDP. And so how do we really balance the technology and society demand and the human behavior? What is your thought on that?
Yeah, I think, well, that is the key issue. Obviously, humans have created this problem, and it's up to us to solve it. Our consumption patterns, human nature, we're not going to change. We consume basically, besides our base needs, we consume for stimulus and status. And those issues, I think, we're going to be forced to pursue them in a different pathway. You can't utilize the earth as a kind of open system of resources for us to consume, because it's a closed system. And so technology will do a lot of things for us. It will give us tools, just like this particular tool, to do things in a more efficient way. My point was, with technology, if we allow the growing demands to not control the growing demands, and these are traditional things like bigger homes, more cars, more air travel. We need to address shifting our GDP pursuits to other ways to satisfy human needs. And there are lots of other ways. It's just dealing with looking at GDP rather than getting it through military spending and through the kind of higher material consumer spending, and getting it through more experiential, less resource demanding experience programs.
Thank you. Thank you. So thank you again for your outstanding presentation. So this is the conclusion of your talk. So we have the next session is just a 10 minutes wrap up for today's workshop. Thank you, Michael.
Well, thank you. I enjoyed it, and good luck, and happy Earth Day.
Yes. Happy birthday.
Yep. All right.
So at this time, I'd like to thank all the distinguished speakers for their presentation. Personally, I enjoy it very much and really appreciate their wisdom and idea suggestion how we should look into the future, what solution we can focus on. So let's reflect back. Right now, I know majority of us are facing the high anxiety and stress dealing with COVID-19. At the same time, the COVID-19 remind us this is a nature evolutions, and that evolution has tremendous impact to human race. But it also remind us how this nature evolution done by human by using technology could have impact to our environments, to our Mother Earth. Especially today, we are celebrating the Earth Day. So in the following, here are some of the slides. CalPlug team has collected as a result of the COVID-19 resetting the society, and give you the highlights, the impact of resetting on the society. So Patricia, the next slide. So showing here is in San Francisco Bay Area as a result of the lockdown due to the COVID-19. So what we can see here is a substantial reduction in the greenhouse gas emissions, especially in the nitrogen oxide and CO2 emission and so on. And because less travels, and while the ozone increase, that is the typical known as the weekend effect due to the less consumption of the diesel fuel by trucking fleet. So the next slide. So showing here is the typical in the Los Angeles area, which is in our backyard. So what you can see here is before and after the resets. After the reset, what you can see here is Los Angeles area become very clean. What I remember by watching news, LA has the cleanest day in the metro cities in the world as a result of the reset. So this reminds us when we think about solving a problem, we have to really look at what is the proper use of the technology? In this case, because we were doing telecommute as a result of a lockdown. When we use the technology, we are still connected in some way and minimizing the unnecessary travels. And as a result, we have really done some work. But we understand it has a social economic impact. So the next slide, look at the worldwide impact in China, in Europe, in Italy. It all show the same message. It reminds us, this is the Earth Day, remind us what human evolution in using technology has profound impact to our nature, to our Mother Earth. So when we reopen the economy, as we are talking about here now, we need to really think about what is a forward path, as Michael just talked about. Different way to think about the using technology and how we can really think about is not about the material, it's about the expectation, satisfaction, experience. And that experience probably come from the human interaction, even we are in the virtual space interacting, sharing some wisdom, and spiritually we share a lot of things instead of just continue consuming, driving for the GDP growth. I think that is a very important message to all of us at this time while we are facing this COVID-19 challenging and difficult time. I think it's a time for us to really sit down to rethink what we have done to the nature, and the nature evolution remind us that is something we cannot fight, we cannot negotiate with. Right? Nature will dictate what we can do if we don't do properly. Right? So I think it's when we move forward, we all need to work together, united, working together, find a solution, and share all these solutions. And as a mankind, as a human species, let's deal with the nature evolution. And we, as one of the species in the nature, we have to do our job and to protect our Mother Earth. So that is my concluding remark for today's events. So at this time, I'd like to remind you, there is a survey available for this workshop. We'd like to hear from you what we can do to improve upon our workshop, and what are the topics you would like to hear from us. And also, I'd like to remind you for the today's presentation, all the material will be available in the website, as well as their presentation. They are recorded. So once we get the permission from the presenters, they will be available. And some of you might have a question and you can send to us. We can forward those questions to the presenter. Then we can also post the Q&A in their presentations. At this time, I want to thank all of you for your participation in this event while we are locked down at home. Please stay safe, healthy, and home. Take care. Thank you.